Deep inside every network that carries video or live streams sits a router with a hard problem. It must copy a multicast packet to many neighbors without ever letting those copies circle back and multiply into chaos. Every multicast stream begins at one place, a source, the server actually sending the packets. Everything downstream is just copies of what it emits, fanning out toward whoever asked to receive the stream. To reason about the source, the router leans on something it already keeps. Its ordinary unicast route table, the same map that tells it which interface it would use to send a packet back toward any address. Downstream wait the receivers, the hosts that actually asked for this stream. The router's whole job is to get exactly one clean copy to each of them and never a flood of duplicates. Together, these paths form a distribution tree, a branching structure spreading the stream outward from the source. A tree has no loops by design, and keeping it that way is exactly what today's rule protects. Because if a loop ever forms, copies feed each other and grow. What began as one stream becomes a multicast storm that saturates links and can take an entire segment down in seconds. That is the stake. Around our router sit neighbor routers, each also forwarding the same multicast stream. Normally, that cooperation builds the tree, but it also means the very same packet can arrive at a router from more than one direction. And there is the danger, a looped copy of the stream arriving on some side interface it was never supposed to come from. Left unchecked, that one stray copy is how the storm begins. Let us watch the rule. A multicast packet reaches our router, sent along from the direction of the source. Before reverse path forwarding, a router might simply copy it out every other interface. That naive behavior is exactly what seeds loops. So instead, the router pauses and asks one question. It takes the packet's source address and looks it up in its unicast route table, the map of how it would reach that source in reverse. The table answers with one interface, the port the router would use to send traffic toward that source. This is the reverse path, and it becomes the single interface on which incoming copies are allowed to be trusted. Now the actual test. The router compares the interface the packet arrived on against that one reverse path interface the table named. Match or mismatch, that comparison alone decides the packet's entire fate. Take the honest packet first. It genuinely came from the source's direction, so it arrived on the reverse path interface. The check passes. This is a real, first arriving copy, and the router accepts it without hesitation. Accepted, the router now does its real job. It forwards the copy out toward the receivers that asked for the stream, sending it down every outgoing branch except the one it just arrived on. From those receivers and the routers beyond them, the stream keeps branching outward along the distribution tree. Each hop repeats the same reverse path check, so the copy only ever flows away from the source, never back. Now the dangerous case. A neighbor router, part of the same delivery, forwards its own duplicate of the very same stream, and that copy comes knocking on one of our router's side interfaces. That arriving duplicate is the looped copy we feared. It reached us on a side interface, not the reverse path one, because the reverse path to the source points somewhere else entirely. So the comparison mismatches. Because the interface is wrong, the router does the one thing that saves the network. It silently drops the copy. Nothing is forwarded, so this stray duplicate dies right here instead of feeding a loop. See why loops cannot survive. Any copy traveling the wrong way around a loop must, by definition, arrive on an interface that is not the reverse path, and every router it meets discards it for that reason. The result is quietly elegant. Each router keeps exactly one copy, the one from the source's direction, and rejects all the rest. Duplicates never accumulate, the distribution tree stays loop-free, and no storm can form. And notice what the reverse path check really is, a gate on the way in, not the way out. It decides which arriving copies are legitimate, and only those legitimate copies are ever allowed to branch further down the tree. Worth a footnote? The table consulted is not always the plain unicast one. Routers can keep a dedicated multicast routing table, sometimes fed by a separate topology, and the reverse path check reads from whichever table is configured for it. There is a real limit. Reverse path forwarding assumes the path back to the source is the same one traffic arrives on. When routing is asymmetric, a valid stream can arrive on an unexpected interface and be wrongly dropped. The check also adapts to the tree in use. On a source tree, it tests against the source's address, but on a shared tree, it tests against the rendezvous point instead, the agreed meeting router the shared tree is built around. The same idea travels well. Unicast reverse path forwarding uses the exact trick to fight spoofing. If a packet's source address could not legitimately arrive on the interface it came in on, the router simply drops it. So the whole picture, a router accepts a multicast copy only if it arrived on the interface it would use to reach the source. Matching copies flow down the tree, mismatched copies are dropped, and loops quietly die. That's how it runs. Next time a stream reaches your screen without stuttering or storming the network, remember the small, blunt rule doing the work. Accept it only if it came the right way. Follow how it all runs for more. See you in the next one.